Hi everyone, my name is Alexandra, and in this video I'll be covering some ways that we can think about evaluating the quality of research studies. Specifically, this is a set of concepts called the Bradford-Hill criteria, and they can be used to strengthen the case that a hypothesized cause is leading to an effect in an observational study. Now remember, we've talked about this a lot, but observational studies cannot establish a causal relationship. Only experimental studies can do that. But the presence of some of these Bradford-Hill criteria can give us more reason to think that that causal relationship might exist in an observational study. But it's important to remember that a study doesn't need to meet all of these criteria to still potentially be describing something that has a causal relationship. And even if a study does meet all of these criteria, that doesn't necessarily mean that the study is describing a causal relationship. So these criteria cannot be used to determine causality. They just give us a framework for how to think about if causality is even plausible. The first concept is temporality. If a study establishes that their hypothesized cause occurs before their hypothesized effect throughout time, that establishes that a causal relationship is at least possible. So the cause has to occur before an effect in order for there to be a causal relationship. We've talked about studies that establish that relationship in prior videos, so let's remember that cohort studies and case control studies, and of course experimental studies as well, establish this temporal relationship. The next concept is strength of association. So over here on this XY axis, I've labeled the x-axis as cause, but let's remember that this is just the hypothesized cause, so we can think of it as our independent variable. And then the y-axis is the effect that we're interested in, and remember that is the dependent variable. So if you're looking at different levels of your independent variable, and you notice a relationship that looks like this, so I'm plotting a scatter plot of all of the data points, you can see that for data points with a lower level of the independent variable, they also have a lower level of the dependent variable. And then for data points with higher levels of the independent variable, there's also a higher level of the dependent variable. Now for this specific data set, we can draw a line through it, and we can see that the line quite nicely predicts the relationship between the independent variable and the dependent variable. This suggests that the independent variable is explaining a lot of what is happening to the dependent variable. You could compare it to a data set such as this green one, and if we tried to draw a line predicting that relationship, it's much less predictive. So for example, this point falls really far away from that line. In this example, the purple data set represents a strong association, and the green data set represents a weak association. Now, one thing that's important to remember is association is not the same thing as causation, or you might have heard this referred to as correlation does not imply causation. So just because the purple data set has a strong association between the independent and dependent variables, that doesn't necessarily mean those variables have a causative relationship. There could be a third variable that's driving a change in both of those variables. However, we can say that the purple data set is more likely to have a causative relationship than the green data set. The next concept is consistency. So if other researchers can do the same study and see similar results, that provides a stronger case for a causal relationship existing. The next concept is specificity. Specificity asks, is there a one-to-one relationship between the presumed cause and effect? So here you can see that the independent variable is driving the dependent variable, whereas in this case, the independent variable we're interested in is leading to changes in multiple outcomes. Now, this makes the mechanism for our independent variable driving our dependent variable a little bit less straightforward because it just seems like there's a whole lot of things going on. But I'm sure if you think back on your medical training, you can think of a lot of examples where a single exposure does lead to multiple systemic effects. For example, smoking or high blood glucose. So you can see how these criteria aren't always perfect. Further evidence is provided for a causal relationship if there is a biological gradient between the independent and dependent variable. This is basically a simplified version of this scatter plot that we looked at before. So let's say in your study, some people have very high levels of exposure to your independent variable, and some people have lower levels of exposure to your independent variable. If the people who have higher levels of exposure experience higher levels of change in the dependent variable than those with lower levels of exposure, that suggests the presence of a biological gradient and provides further evidence for a causal relationship. And a special case of this is reversibility, where if you take the cause away entirely, the effect goes away. The last four criteria are a little more ambiguous, but we'll go through them quickly. So plausibility asks, is there even a conceivable way that our proposed exposure can be leading to this effect? But you can imagine that if a scientist is imaginative enough, they can come up with some way that that mechanism might be occurring. Coherence asks if the study results generally agree with what is currently understood about the variables being studied. However, it's sometimes really important to pay attention to studies where the study results seem to not agree with current scientific consensus, because those studies can reveal gaps in our knowledge. Experimental evidence refers to if there are studies in animals or cell models or other more basic scientific models other than humans that support the research. So, for example, if you're saying we think observationally this exposure causes this effect, and you look in the literature and you see that there was a scientific paper looking at that exposure in mice and it drove the effect that you're seeing, that gives you good reason to think that causal relationship could apply to humans as well. Finally, we have analogy, which asks, have similar independent variables been shown to lead to changes in similar dependent variables as the one you're studying? But you can imagine if a scientist is creative enough, they can come up with an analogy between their study and just about anything else. So I don't think this study criteria is quite as strong as these earlier ones that we've talked about. All right, and that brings us to the end of the content for this video series on research study designs.